Thank you, Mr. Chairman, for the introduction. Dear ladies and gentlemen, welcome to the presentation about squeezing ground conditions. The conference paper was written together with my colleagues of Implenia as a contractor and also with IGT, Mr. Zafer Ekici, who was the responsible designer when this type of healing element was used first. When we talk about squeezing ground conditions, then we mean conventional tunnel excavation, for example, NATM. And this is always combined with large and often long-lasting displacements. So we are in a rock formation of very weak ground conditions and mostly with a high stress state. You can see here one example where you see a pilot tunnel which was constructed beforehand to make some pre-relaxation. Here already you can see large displacements. Then in the next step, the main tunnel was constructed, also with large deformations, larger than 1 meter. And here the clearance profile was not fulfilled anymore. There have been some cracks in the shotcrete lining, and the tunnel had to be built a third time. And of course, we would like to avoid such situations. And this brings me to the next step, why we should use a ductile lining system, for example, with yielding elements. You can see here a ground reaction curve showing on the y-axis the support pressure, on the x-axis the radial deformation. We start with a high initial in situ stress state, and with increasing advance of the tunnel, the excavated space starts to deform, and the support pressure which is required is reduced. So we have elastic deformations, and in such ground conditions also plastic deformations. If we would now apply a stiff shotcrete lining, this would in many cases be not economic or even not possible. You would need shotcrete thicknesses, for example, larger than 1 meter to find equilibrium within the ground. And as we have heard in the previous lectures about carbon footprint, we should find a solution where we need less shotcrete concrete to be more economic. And therefore, the so-called yielding principle is applied in such ground conditions. This means we allow a certain amount of deformation, and with this we can reach equilibrium with the ground with a reduced support pressure. The only two things you have to consider here, you have make some over excavation to finally fulfill the clearance profile, and on the other hand you need a lining which is capable to take the high strains of this deformation of the tunnel. One example of such a system is a ductile shotcrete lining with yielding elements. You can see here an example of a top heading advance with 4 rows of yielding elements, and in detail B how this looks like in detail, how these yielding elements are installed and integrated into the shotcrete lining. How does this system work? What's the principle of this system? We have the installed yielding elements in the shotcrete, and they should take the strains which occur from the rock mass. Because, especially after the first few days after excavation, if we have large deformations, the shotcrete strength is really low and the displacement rate is really high. And in this case, the yielding elements, they have to absorb the largest amount of displacements, that the shotcrete does not get any failure or cracks. Then, usually in the rock mass we have more or less radial deformations, also sometimes anisotropic, of course, in such conditions. But these deformations, they have to be transferred to a circumferential shortening of the lining. Means most of the strains have to be taken by the yielding elements. You can see here one example picture of a tunnel where you see several rows of yielding elements installed, a dense bolting to harmonize the displacements and the shotcrete segments. we as a contractor, we have been faced with several tunnels with squeezing ground conditions, and we had to install thousands of these yielding elements. And for modern tunneling, yielding elements have been developed about 30 years ago, but they all of them consist of steel, concrete, or a mixture of both. This means they're really difficult to handle on site, and we were thinking of how can we be faster and more safer for the installation process. We started a research project and looked to alternative materials, and then we came up with this Hs-Eps, a high-strength expanded polystyrene, which is a special type of polystyrene which can take the high stresses and high strains occurring in tunneling. You can see pictures of the first initial laboratory tests on a really small scale, and at this animated graph, which was analyzed with digital image correlation, you can see a formation of a horizontal compaction band in the center of the sample. The high strains here are taken through inner compaction of the material, and you can also see that the Poisson ratio is extremely low. This type of material has an inherent stress-strain response. It consists of a linear elastic phase, a long yielding phase in the central part, and finally a densification phase. And this was exactly what we've been looking for. If you can remember the support reaction curve I showed you beforehand, we need a range where the shotcrete has time to cure and where we have to take largest displacements. And this is here in this yielding phase. But finally, we also want to reach equilibrium with the ground, and therefore we need this final densification phase. In the next step, we started a research project on a larger scale. We produced panels with 5 centimeter thickness, glued them together, and we could produce a really lightweight yielding element with 10 to 20 kilogram, depending on the configuration and the size which is needed. And we saw that the yielding elements are capable to take the high strains. What's also important and interesting, that it's a really flexible approach. It's some kind of a sandwich construction. This means by changing the density of the single panels or combining different density panels, there's a high flexibility regarding the stress-strain response, which you can see here at the green shaded area. This is important for the designer because there is no one global yielding element which you can apply in every tunnel around the world. It's really project specific, and most of the time you also need different yielding elements and stress-strain responses at one project, because you have to think of how fast are my displacements, how large are the displacements, what type of shotcrete do you use, what's the advance rate, and depending on all these types and parameters, you really have to make a project-specific design. And just by rearranging the panels, this can be done within short time. The first application was at the Semmering base tunnel in Austria, which is currently under construction. The last 650 meters are missing there. Then the 27-kilometer tunnel will be finished, hopefully next year. There we hit a fault zone composed of cataclastic mica schist with just moderate overburden of 160 meter. And together with the designer, we decided to make a test section for this new type of yielding elements. We installed 4 rows of them. This is the prototype we produced. You can see the length of the yielding element is 80 centimeter, capable for 1 meter round length, because you also have the lattice girder. It's 30 centimeter in height and 25 centimeter the thickness according to the shotcrete thickness. In such ground conditions, of course, you have to apply the observational approach with monitoring data interpretation and daily monitoring. You can see the installation of the 4 yielding elements, and with this displacement vectors, we could measure 210 millimeter of displacements. This means it was a good decision to use and apply a ductile shotcrete lining, because probably with a stiff lining it would get cracks or would fail. And what you can see here at the intersection and deviation of these vectors, that the strains are taken by the yielding elements and not by the shotcrete. So exactly what we would like to have. Nowadays, these new yielding elements applied in several tunnels. You can see here an example with a pilot tunnel, which is equipped with 6 rows of these Hs-Eps yielding elements. Here in this pilot tunnel, displacements of larger than 1 meter occur, and since it is used as a pre-relaxation, the configuration is really soft of these yielding elements. And finally, the main tunnel can be constructed here, for example, with 8 rows of these yielding elements, and also again 50 centimeter up to 100 centimeter of deformations occur here in the main tunnel. And with this combined system, using a pilot tunnel and applying the, let's say, optimized stiffness or stress strain response of the yielding elements, a dense bolting pattern, and a really flexible construction process, it is even possible to tunnel as economic as possible and as safe as possible in such really difficult ground conditions. To wrap up, for us as a construction company, for the contractor, the most important thing was that the yielding element is lightweight. This means it's safe for installation and we are fast for installation. As you can see, even I can lift such a yielding element with 10 to 20 kilogram, and in about 5 minutes you can install it. For the designer, the flexible stress strain response is essential, because he can be extremely flexible if ground conditions, for example, change, or also from his design perspective, he can say which stress strain response he needs to get a good utilization of the lining, and we can design this tailored. The flexible sizing is another important thing. If you have, for example, 1 meter round length, geological conditions get worse, you have to reduce the round length, you can simply cut the yielding elements with a saw directly on site, and you don't have to stop and order a different configuration. And the last point, a high resistance against tilting. Heterogeneous fault zones are prone for anisotropic displacements. That is what we really often see, that we have not these radial displacements, high anisotropic deformation patterns, and if you have a full surface load transfer with this type of yielding element and a high flexibility, so even the single panels can shift, then you get this high resistance against tilting in case of anisotropic displacements. I would now finalize my presentation with a few pictures of the tunnel, and these are not arbitrary pictures. These are all teams of Slovenian guys which are worked together, and they made a really good job here at the Semmering base tunnel. And I would like to finalize, say thank you for your attention and Glück auf.
Thank you, Manuel, for this very interesting lecture. Are there any questions from the audience? I will help a little bit. The last sentence of your lecture was about anisotropic conditions, and we had them in Karavanken tunnel, and sometimes obviously the high yielding elements wouldn't cope with such level of anisotropy. What would be your advice in using this type of Hs-Eps elements in anisotropic conditions?
I think if you have anisotropic displacements, one important thing is to reduce the height of the yielding elements. They should not be too high, because otherwise they are more prone. If the slenderness ratio is really high, they can start initially to tilt. And from our experience, it is good to have this full the full surface load transfer means you need a yielding element which has a good geometrical shape. And from our experience, reducing the height and the slenderness ratio really helps a lot. And of course, you should also apply close above and below the yielding elements rock bolts.
Yes, I mean, they come in fixed lengths, so you can't easily reduce, but this one probably you can. Yeah.
Yes, you can even make a different configuration on site. They are simply glued together.
Okay. Thank you. Any other? Yes, Alan, please.
Thank you for a really interesting presentation. Just looking at the pictures there, there's a lattice girder every meter, 1.3 meters. And then that's sprayed in, so you end up with a stiff line. Do you need the lattice girders? Could you use a fiber reinforced lining and then have a more continuous sort of softer lining?
Yes, of course. The combination would also be possible with a fiber reinforced shotcrete. And in this case, the lattice girders, they are used, of course, to have a good shape of the tunnel. And in the next step, also for the installation process of the yielding elements. You can, if you see here, for example, these lattice girders, there is a steel bar fixed between the two lattice girders, and this is for the installation process of the yielding elements to be really fast. But the lattice girder is not a really stiff support element here in this type. Compared to the yielding elements, it's really soft. If you have large deformations, at the first few centimeters, of course, you have some resistance of the lattice girder, but then they immediately start to buckle at the position of the yielding elements, and then the resistance is relatively low, so it's also a ductile system.
Thank you. Still a lot of steel gets put in, but thanks for the explanation.
Thank you. Any more questions? Yes? We have just time for another one.
I have a question about fire resistance of those EPS elements. Can fire endanger the construction or not, because it's hidden in concrete? Thank you.
Yes, of course, we also had a look on that. And if you put a flame directly on this EPS material, then it starts to burn, yes. But as soon as you remove the flame, it is self-extinguishing. And we were talking with the client and the designer about this aspect. And we all agreed, if you have a fire accident inside the tunnel, you generally have troubles, yeah. But not just with the yielding elements, you will also have trouble with the shotcrete and the spalling of the shotcrete. And usually, after 100 meter or 200 meter behind the face, you add a sealing layer or a second layer of shotcrete, and then they are integrated into the shotcrete, and then it is not a big issue anymore. So this was how we proceed at the construction sites where these yielding elements are nowadays installed. We all think the fire case is not the most important, but in the back, of course, you have to think on that. And it can, of course, be one issue if you have an accident in front of the face, that there might be a problem from a static point of view, but also you have this problem with your shotcrete and the spalling of the shotcrete.
Thank you.
Okay, thank you, Manuel. Thank you for this.